of our fundamental theorem of calculus. Again, by now we should be comfortable with the integration sign. And again, we should all know exactly what this integral from 0 to 2 of f prime of x represents. We know that this is going to represent the area under the curve over your interval 0 to 2. So even when we dive into the algebraic ways of finding integration, that hasn't changed. It's still an area under the curve. Again, remember, when we're talking about integration, it's a total. It's an accumulation over time versus derivatives are a rate. So what happens is when we integrate a derivative, we are undoing the derivative and we are getting back to the accumulation and the total. So we focus primarily on finding the exact area where it was a nice, pretty. We could just take the region under the curve, divide it into triangles, divide it into rectangles, divide it into semicircles, add those different areas together. However, not every shape is going to fit into a perfect geometric shape. So what's going to end up happening, one theorem that's going to help us figure out the exact area is the fundamental theorem of calculus. So in other words, when we talk about the fundamental theorem of calculus, we're looking at a definite integral. When I say a definite integral, you have an upper bound and you have a lower bound. You have constants or a variable, as we saw when we were doing the second fundamental theorem of calculus. So what we're going to do then is, again, when we integrate g prime, then that's going to get me back to whatever function g is, and I'm going to plug in my upper bound minus the lower bound. That is your fundamental theorem of calculus. When we study derivatives, one of two things could happen. One, your answer was just a numeric answer. In other words, I asked you to find f prime of 3. So you would find the derivative and then you'd plug in a 3. Or I asked you to find f prime of x, which meant your answer was just an equation or just a function. Same thing with integration. When you have a definite integral, for example, with those bounds of 1 to 5, your answer is going to be a numerical answer. This is how you evaluate an integral. You have to use the fundamental theorem of calculus. So for example, you still have to make sure your bounds are proper. So for example, when you take a look at b, I know that my lower bound and upper bound are not proper. So I'm going to have to first negate my integral and rewrite this as my integral going from -2 to 5 of h double prime of x. Before you apply that fundamental theorem of calculus, again, you've got to make sure you get those bounds proper. Now, what do you think is going to happen if I integrate the second derivative? That's not going to get me to h of x. That's going to get me to h prime of x. So then again, you have to keep your negative sign outside a set of parentheses. So then when I apply my fundamental theorem of calculus, I know to evaluate this integral, it's going to be h prime of 5 minus h prime of -2. Folks, parentheses have got to be your friends here this year, especially when you're rewriting these bounds. You've got to make sure, folks, that you figure out the difference between h prime of 5 minus h prime of 2, and then you're going to negate that answer. So just make sure if you do have to switch your bounds, just make sure that you have parentheses around that h prime of 5 minus h prime of 2, or you distribute the negative sign all the way across. All right, so that is your fundamental theorem of calculus. So again, when we talk about your fundamental theorem of calculus, when you integrate a rate, then I know that when I plug in my upper bound, it's going to be my f of b minus f of a. That's how you'll get a numerical answer when you do your integration. Without the numbers at the top and the bottom, without the bounds, we call that an indefinite integral, which we'll take a look at here in a few minutes. So here's a table question. Notice in my table question, I have a bunch of values for uppercase f, lowercase f, f prime, and f double prime. So let's take a look now at evaluating this integral from 1 to 6 of f prime of x. So again, I know when I integrate f prime, that's just going to give me f of 6 minus f of 1. So again, when I integrate f prime, that gets me back to f. So again, from the table, when x equals 6, f of 6 is going to be -3. Minus, when x is equal to 1, f of 1 is 2. So my answer is going to be -5. So any questions on how you can use a table to help you evaluate a definite integral? So now if I take a look at b, the first problem is, are my bounds set? No. So the first thing I have to do is I have to rewrite using my bounds. Also, and we're going to talk more about this, if you see a constant inside your integral, you want to yank out that constant, just like you do with derivatives. Just like we pulled the constants out, we differentiate the function. Same thing with integration. So I'm going to rewrite this integral as from -2 going from 3 to 13 of f prime of x. So then I'll concentrate on integrating f prime. So again, when I integrate f prime, that's just going to leave me with f. So what I want to do is take that -2, pull it out, and then I'm going to figure out what f of 13 is minus my f of 3, and then I'll multiply by -2. So then from the table, f of 13 is just going to be 10. F of 3 is just going to be 7. So follow your order of operations. I want to subtract 10 minus 7 first, which will give me 3, and then multiply by -2, which is -6. So just be careful when you're pulling out those negative and constants. Make sure you follow your order of operations. Simplify inside parentheses first, then multiply by the constant or distribute that negative sign. Okay, so any questions on B? We're going to skip over C right now because we're going to talk about how to integrate a constant here in a few minutes. So let's go ahead and take a look at example D. So for example D, first of all, what's the problem? The problem is what? I'm going to have to do what? Switch my bounds. So I know it's going to be 1 to 7 of f double prime of x dx. Now, when we integrate the second derivative, what is that going to get us back to? That's just going to get us back to the first derivative. So again, I'm going to keep that negative sign factored out. I know when I integrate f double prime, that's going to leave me with f prime of 7 minus f prime of 1. So any questions on how I've plugged in my upper and lower bound and used that second fundamental theorem of calculus? Again, follow your order of operations from the table. When x equals 7, f prime of 7 is -3. So I have -3 minus, and again, f prime of 1. So when x is equal to 1, f prime of 1 is 8. And don't forget about your negative sign in the front. So we have -11, which is just going to leave me with an 11. Okay. So any questions on that particular one? All right, let's take a look at a graph one. Now pay attention to the graph that's given. Notice this is the graph of g of x. Not g prime, but g of x. Always pay attention to the graph that's given. So when I take a look at this particular integral, my bounds are good in 3a. So I'm going to apply. So what happens when I integrate g prime? When I integrate g prime, that's just going to give me function what? G. So I'm going to worry about g of 3 minus g of -1. Now, since I'm given the graph of g, remember, be careful with the graph questions. It's either going to be area, point, or slope. So since this is the graph of g, how am I going to calculate g of 3? Is this area, point, or slope? Point. So then on the graph at x equals 3, I know the y value is 1 minus g of -1. Again, I know when x is equal to -1, the y value is 3. So the answer is going to be -2. Now let's take a look at B. First of all, you got a problem. Because what's the problem in letter B? You're going to have to do what with your bounds? You're going to have to switch them. So again, I'm going to have to rewrite this from -1 to, the negative integral from 1 to 6 of g of x dx. Now remember, it's the graph of g that is given. So when I integrate, again, this is where they use that uppercase letter. If it's not necessarily written as a derivative, we're going to use the uppercase letter of g to represent that g is the integral. So I'm going to rewrite this as a negative quantity, g of 6 minus g of 1. Now, since when I answered part A, g of 3 was a point, when I integrate g, what do you think g of 6 is going to be? Area or slope? Area, exactly. So what I'm going to have to do to find g of 6, I'm going to calculate the area under the curve from 1 to 6. So again, the area under the curve from 1 to 6. So again, I'm going to calculate the area of this rectangle and add it to the area of the triangle. So I know the area of this rectangle is going to be 6 times 1, which is 6. The area of this triangle is going to be 1/2 base of 2 and then height of 2. So the area of that particular triangle is just going to be 2. So then what I know then is g of 6 is going to be the area under the curve from 1 to 6 of g of x dx, which I know I can add together to give me 6 plus 2, which is 8. Minus. Now I'm going to have to calculate g of 1. So g of 1 is going to be the area under the curve from 1 to 1 of g of x dx. And what's that area going to be? What happens when your bounds are equal? 0. So this is just going to be negative 8. Yeah, so like I said, yeah, that area, that rectangle should be 5. So 5, so that's going to be negative 7. And again, we're going to talk about how to integrate constants here in a minute. So now let's talk about the indefinite integral. And like I said, we're going to, just like you learned a whole bunch of derivative rules, you're going to have to learn a bunch of integration rules. So when we talk about an indefinite integral does not have a lower bound or an upper bound. So the question we ask ourselves is this. Up till now, I've been giving you a function and I've been asking you to find a derivative. Now we're going to go backwards. I'm going to give you a derivative. What I want you to answer is what function has a derivative of 3x squared? There's more than one correct answer you could come up with. Wouldn't you agree with me that the derivative of x to the third plus 1 is 3x squared? Wouldn't you agree with me that the derivative of x to the third minus 7 is 3x squared? So notice the x to the third plus any constant is going to give me that derivative of 3x squared. So again, when we're looking at, so instead of writing what function would have a derivative of f of x, we write it as the integral sign. But that's what it means. Whatever is inside the integral, that's the derivative. What we are trying to find is the function that has the derivative. That's why the integral is what's also called the antiderivative. You are undoing a derivative. So that's why, because of the reason that I just illustrated, all three of those examples all have the same derivative of 3x squared. This is why when you integrate an indefinite integral, meaning you do not have an upper and lower bound, you have to add a c to the end, because there could, even a constant can be 0, because there could be a number that was added to that particular function, like I illustrated up here, that will have that particular derivative. Now, there will be cases where they'll give us an initial condition where we'll be able to solve for c, but they're not going to give us those initial conditions all the time. And yes, you do lose points if you forget to add your c. You ever heard the song Let It Be by the Beatles? Well, we're going to change the words on that a little bit to add the c. So we'll do some singing later on when it comes to adding the c. So like I said, when you're taking an indefinite integral, you must always write a plus c. Just like we have a song for Riemann sums too. We'll be doing some singing when we come back from Thanksgiving break to review for our first test. All right. So some basic integration rules you have to know. Well, what function, by the way, if I asked you to integrate 0, what kind of function has a derivative of 0? Any constant. So that's what the c represents. Because if you take the derivative of any constant, you get a 0. Now, let's talk about integrating a constant, just a plain old number. For example, what kind of function would have a derivative of just 7? 7x, but plus your c. So when you integrate just a number, it's just going to be 7x. So I know in your previous homework problems, I asked you to integrate a constant. I said, well, just draw your horizontal line, for example, y equals 7, sketch the area and find the area of the rectangle. You don't have to do that anymore because now you know the fundamental theorem of calculus if this was a definite integral. As I mentioned a few minutes ago, if you have a constant inside your integral, pull it out just like you do with derivatives. And I mentioned this as a property the other day. If you see addition or subtraction inside your integral, separate it. Integrate term by term. Or if it's subtraction, same thing. Folks, this is going to be a must. Some of you are going to fight me on this and you're not going to like it. If I had $1 for every time somebody didn't want to do this and then end up with the wrong answer, I would not be teaching anymore. I'd be living at my beach house. Those of you, this is where constants are going to start driving you nuts. That's what makes integration a little tricky. Because what happens is if you don't split your integrals, some of you are going to start yanking out constants, and it's going to give you the wrong answer because that constant doesn't apply to every term in your integral, especially when we get to integration by parts, which is a topic that you did not do in AB last year. If you are not in this habit of separating your integral, when we get to that trickier integration, those constants are going to be very challenging. Get used to splitting your integrals now so you don't make these mistakes with constants. Now, the big one we're going to focus on today, you learned the power rule for derivatives. We have a power rule for integration. So if you have a base of x raised to an exponent, it could be a fractional exponent, it could be a negative exponent. We know with a derivative, we subtract 1 from the exponent. Remember, we talked about this the other day. Derivatives and integrals are inverses of one another. So instead of subtracting 1 from the exponent, we're going to add 1. And we knew from derivatives, once I subtracted 1 from the exponent, I multiplied that base of x by that exponent. Well, instead of multiplying, we're going to divide. So you add 1 to the exponent, and then you divide by the new exponent instead of multiplying. It's the inverse of what we did with derivatives. So that is your power rule for integration. So let's take a look at this first example. Let's find your integral of 3x. Well, first of all, I can pull out a 3. So I can yank out my 3 and worry about integrating x. So again, using my power rule, remind me again, what is the exponent for x? The exponent is just a 1. So I know I'm going to add 1 to that exponent. So that's going to give me x squared. And then I'm going to divide by 2. And don't forget to add your c. And you can always check your answers. Because if you take the derivative of your answer, so if I wanted to take the derivative of this answer, I know the derivative is going to give me 6x over 2, and I know the derivative of any constant goes to 0. That gives me 3x, which puts me right back to the same integral. So you can always check your answers by taking the derivative, not that you're going to want to. Just like we did with derivatives, there are going to be cases where you have to do some rewriting. Like I mentioned, we don't have a quotient rule for 1 over x to the third. So what I need to do is I can rewrite this. I can rewrite this as x to the negative third dx, just like I did with derivatives. Get that variable out of the denominator. Now I'm ready to go ahead and use that power rule for integration. So I'm going to add 1 to my exponents. That's x to the negative second divided by negative 2 plus c. And again, if you wanted, you don't have to simplify this, just like with derivatives. But if you were, this would be negative 1 over 2x squared plus c. But just like with your derivatives, you do not need to get rid of the negative exponents. Any questions on B? Let's take a look at C. Just like with derivatives, if you see a radical, you've got to change it into a fractional exponent. So I know that I can rewrite the square root of x as x to the 1/2 dx. Now I can apply that power rule. Remember, I'm going to add 1 to that exponent. And what is 1/2 plus 1? 3/2. Now, when I divide by 3/2, what is that equivalent to? That's equivalent to doing what? Multiplying by the reciprocal. So this is actually 2/3 x to the 3/2 plus c. Get used to that in your mind, folks. Dividing by a fraction, you multiply by the reciprocal. Because more often than not, you're going to have fractional coefficients when you're doing a lot of these problems. So any questions on integrating the square root of x? Now let's talk about letter D. I know I'm taking the cube root of x and multiplying by x minus 4. Like I said, there is no product rule. I couldn't do fig figgy if there was one out there, and I'm not hiding anything from you. It doesn't exist. But what algebra could you do here? Distribute. I can distribute that x to the 1/3. So remember that cube root of x is actually x to the 1/3. And just like I did with derivatives, what I could do is I could distribute that x to the 1/3 before I do any integration. Now, remember when I multiply like bases, I add those exponents together. So what is x to the 1/3 times x? That's going to give me x to the 4/3 minus my 4x to the 1/3. Now I have subtraction inside of this particular integral. So again, I can integrate term by term. So x to the 4/3 dx minus 4 I can pull out, and then I can integrate x to the 1/3 dx. So go ahead now and integrate term by term for me. Going to be a handful of you that don't want to listen to me. Will get yourselves in trouble. Suppose, what if I gave you an integral that looks like this? So I ask you to integrate something like this. This doesn't look too hard. I see I'm going to pull out this constant. Is that equivalent? No. This is where some of you will run into trouble because you're going to see that 2 or you see that constant and you yank it out and then you just want to integrate term by term. Remember, those are not equal. That's why I want to get you now in the habit of separating these integrals before these integrals get too complex. Because if you start pulling constants out before you separate these integrations, you're going to make careless mistakes with these constants. That's where most of the mistakes come from. It's not the power rule. The power rule is not that hard. It's going to come from these constants because you start yanking them out too soon before you actually break up the integral. So you've got to be really careful with these constants, especially when we get to integration by parts later on in this particular unit in the second part of Unit 6. So just be careful with those constants. Yeah. Derivatives. Again, we do not have a quotient rule for integration, and I'm not hiding one from you. But remember, we did this with differentiation even before I gave you the quotient rule. What can you do with this larger fraction? You can take this larger fraction and do what with it? You can split it up. Remember, you can take this larger fraction and split it up into 2 smaller fractions. So I can take x divided by, again, square root of x is just x to the 1/2 plus 1 over x to the 1/2. So just like with differentiation, if you have a single x in the denominator, what you can do is you can split up this larger fraction into smaller fractions. And again, before you do your integration, use your properties of exponents and simplify your fractions. What does x to the 1st divided by x to the 1/2 simplify to? That simplifies to x to the 1/2. Plus, I've got to get that x to the 1/2 out of the denominator, so I can write that as x to the negative 1/2. Now I'm ready to go ahead and integrate term by term. So go ahead and do your integration there. Are we okay on letter E? Again, remember when you divide by 3/2, you actually multiply by the reciprocal, and that's where we get the 2/3 from. Okay. Questions on E? What algebra do you think I'm going to have to do in letter F before I can do my integration? FOIL it. So I have to get rid of the parentheses. So I'm going to have to take t squared plus 1 and multiply it by itself. So get rid of those parentheses. So again, when I FOIL, I'm going to end up with t to the 4th plus 2t squared plus 1 dt. So go ahead and integrate that for me. Put it on a test. I put it on the quiz. I can't tell you how many students get so stumped by integrating dt. What number is actually in there that you're never going to see written? A 1. So what function has a derivative of 1? X, or in this particular case, it's going to be a t. So don't forget, when you integrate just plain old dt, you actually have the constant of 1 in there. And the question you ask yourself, what function has a derivative of 1? So again, you just don't be alarmed by it, but it just stumps a lot of you. So just be careful about that. I think at the beginning, just like when we had to do the derivative of x, some of you were stuck on how to do the derivative of x. And then eventually we did enough where I recognized that it was a 1. But just again, remember when you integrate that dt, it is going to be a 1. Questions on that? All right, last thing. One thing about constants, and this is the whole purpose about example 2a. Look at example B. What constant could you pull out? 2/3. So sometimes your constants, remember, are going to be fractions. So always pull out your constants, even if those constants are fractions. What constant can I pull out in letter C? negative 9/5. So negative 9/5 times 1 over x to the 4th. So just remember that when you're doing your integration and pulling out constants, those constants may be fractions. So yank them out before you actually do your integration. All right, so any questions? So that's basically just the power rule.